Okay, so let's finish up our discussion on the confinement factor for LP modes that we started last time. Right, so we calculated this quantity eta, which is the fraction of the power being guided in the core, right? And then we derived this expression for the confinement factor, right, which depends on which mode it is, right? So, right, it depends on L here clearly, and of course it also depends on M because this U and W are dependent on M, right? So which mode it is. Right, so let's try to make sense of this question a little bit. So at cutoff, right, so just when the mode is stopped being guided, right, which means the effective index becomes equal to the index of the cladding, right? So basically, cutoff means effective index is cladding, right? Which means this propagation constant or the normalized propagation constant is going to 0, right? Or in other words, in terms of this W and B, W is going to 0 and U is going to B. Where B is the cutoff value. Okay, so basically, so you can see the first term will go to 0 at cutoff, right? W is 0. And for the second term, to see an estimate, so we can try to estimate this function, the limiting value at W equal to 0, right? Again, so this factor will become 1, right, at cutoff. So we can use these limiting values. So for K naught, as W goes to 0, the asymptotic value of the function is just log of W. And for other K values, okay, it approaches that value. So this is L minus 1 factorial, and then we have 1 over 2 over W raised to L. Okay, so you can use these limiting expressions here, right? And you can see that so the confinement factor then approaches 0 at cutoff for L equal to 0 or L equal to 1. Right, which sort of, I guess, intuitively makes sense, right? So at cutoff, the mode stops being guided, it leaks totally into the cladding, so the confinement factor should go to 0, right? But the interesting thing is that for L greater than 1, the confinement factor actually doesn't go to 0. Okay, from these limiting expressions, so you can see that we have L minus 1 factorial here, right? So we'll get L minus 1 factorial square here, we'll get L factorial and L minus 2 factorial. So we'll be remain left with L minus 1 over L. So actually the confinement factor, you can see, approaches some finite value at cutoff. Right, it actually doesn't approach 0. So for the higher order modes, the mode stops being guided much before like your confinement factor goes to 0, right? So that's sort of interesting. Okay, so we can basically try to plot this function for different modes, see how it looks. Right, so we'll get some curves like, for example, the BV curves that we had for different modes, right? So similarly, we'll have confinement factor for various modes as a function of V number. So again, confinement factor will go between 0 and 1, right? So okay, so for LP01, like the lowest order fundamental mode, right? So that exists for all values of V, right? And so the limiting value is 0, L equal to 0. So it starts from 0 at cutoff. So cutoff is basically here, there's no cutoff. So it starts from 0 and then smoothly increases as V number increases, right? So the confinement factor goes up, right? And as you increase V number, so remember V number is like proportional to the core size divided by the wavelength, right? So you can think of this as for a fixed wavelength, you're increasing core size, so the mode is more confined into the core. So that's LP01. The next mode is LP11, right, which starts from this 2.4 here. And so for LP11 also, L is 1, so the confinement factor starts from 0. And this goes like that. LP11. Right? And for any particular V number, you can see that LP01 is more confined than LP1. Right? So that's true in general, right? Any lower order mode will be confined better than a higher order mode. Now, if you look at LP21, okay, so that starts somewhere here, like at 3.8, the root of J1. Okay. So LP21, L equal to 2, right? So that means actually the limiting value is 1 minus 1 over 2, so half. So at cutoff, actually the limiting value is half. Okay, so the confinement factor starts from this value half and goes up like that. Okay, so this is LP21, right? So you can see that the mode stops being guided at eta equal to 0.5 or 50% power in the core itself, right? And then you don't have values below that. Now LP02 also has the same cutoff as LP21, but LP02, the confinement factor starts from 0, so it starts from here. So this is LP02. Now, for example, now if you look at LP31, again L will be 3, so this is 1 minus 1 by 3, so that's 2/3, right? So that's somewhere here 0.66. Okay, so LP31 starts being, that's LP31. Okay, and then LP12 again will be something like this, because L is equal to 1, it will start from 0. Okay? Yeah. Yeah. So the most interesting thing here is that at cutoff, the confinement factor for higher order nodes, like for L greater than or equal to 2, doesn't go to 0. Right? Naively, you would expect that so one limit is when the node is completely guided in the core. So confinement factor is 1, which is what all the curves approach for very high V number. But then as you go towards cutoff, you would expect it to go down to 0 slowly, right? So the mode keeps going into the cladding, and then eventually it's completely in the cladding. But you can see that for some modes, actually, they stop being guided even before, much before you reach 0. Okay. So yeah, that's the discussion on confinement factor. So now let's try to estimate. So we have this V number, right, which sort of gives us some idea about the number of modes, right? As you see, as the V number increases, we have more and more modes which start to exist, right? So given V number, is there a way to estimate sort of how many modes we have in terms of V? So we can do that for high V numbers. So we'll take a look at that. So let's say if you have a highly multi-mode fiber, right? So V number is large, then we can estimate how many modes exist. But for very low V numbers, right, we see that basically we have to go by the roots of these Bessel functions and see some particular root is below or above the value of V, right? But for very high V numbers, for highly multi-mode fibers, we can use sort of the limiting expressions or the asymptotic expressions for the Bessel functions, and then try to estimate the number of modes. Okay, so again, this analysis would be valid, for example, for V numbers sort of greater than 10. Right, below 10, basically, we can just count the number of modes, right, from the roots of the Bessel function. But for large V numbers, like for example greater than 10, we can just sort of approximate the number of modes like this, because then it will become, for these large numbers, it becomes tedious to count one by one, like all the Bessel functions, right? How many roots they have. So basically, if you go back to this, when we were plotting this transcendental equation, right, from which we were calculating the modes, right? So we had so the transcendental equation looked something like this. Right? So for example, the RHS went something like that, right? And on the left hand side, so went something like this, right? So whenever the denominator, we encountered the root of the Lth order Bessel function, it went So it diverges, right? So we are looking at large V numbers, which means we'll have many intersections, as you can see, right? So we'll have many, or in other words, many roots of this Bessel function, right? So like we have many intersections here. So every time you can see that every time, so after the function, so this is the left hand side, solid lines are left hand side is the solid line, right? So every time the left hand side crosses 0, you encounter a mode, right? Before then it diverges, and then you start again it crosses 0, again you encounter a mode, right? Again, same thing. So sort of roughly you can see the number of modes are equal to the number of times it crosses 0, right? Or in other words, whenever the function diverges, just before that you get a root, right? So here, just before the divergence, right? So we can say, for example, so roughly the number of modes, so m, right? So this is for a particular value of L, right? The number of intersections we get are basically the number of m values we get. So the number of modes for a particular L is basically roughly the number of this Bessel function, right, in the range zero to the V value, right? So remember basically U, so as we change B from 0 to 1, this U goes from V to 0. So in this range of U from 0 to V, we want to find the number of roots of this Bessel function, which will tell me how many times it diverges, and that's roughly equal to the number of roots. Okay. So again, if we have a large V number, so that we have many intersections here, right? Or in other words, we have many roots. So we call the Bessel functions look like this, right? So basically, we are saying it. We encounter many roots, right? So we are sort of in the limit where this is J L X, right? So we are in the limit when X is very large, right? So we have already encountered many roots, right? So we can use the asymptotic forms of the Bessel function. So we call that. It looks something like this, right? We can be estimated like, so for large values, it sort of almost becomes like a sinusoidal function, which is damped, the amplitude is damped, right? Right, for U much greater than 1. Right, so again, basically, so U goes up to V. So again, if V is greater than 10, then U values are taking values much bigger than the limit we are working in. So basically, so now we want to see, so if we approximate the Bessel function with this function, we want to see in this range how many. So from this function, we can easily estimate the number of roots, right? Because now we have a sinusoidal function. So we know that every time we increase the argument by pi, we encounter another root, right? Because the sinusoidal functions are periodic with 2 pi or like half periodic with pi, which means every time they cross 0, every time the argument increases by pi. Right, so the number of roots here m, right? That's just the, so the range it goes up to is b, right? So how many times it crosses b? So right. So this argument here goes up to b, right? And so that maximum value basically how many times you're crossing pi, or how many pi steps you are taking. Right? Every time you have pi, we have a root. Right? So we just divide. So this is the maximum value we're going up to, and we just divide that by pi to get the number of zero crossings. Okay, and again, if b is large, right, greater than 10, for example, pi by 4 is a number less than 1, so we can just neglect that. Okay. So okay, we end up with that. So we sort of take this to the other side, and we get, so this condition, indices m and l. Okay, so for given fiber with a given V number, the range of m and l can be such that this equation is satisfied. Right? So for a given L, you can estimate how many m values there are from this equation. Right? So of course you can see that for lower L values, there will be more number of m values. Again, which is sort of expected, right? And as you increase L, the number of m values for that particular L goes down. Right, so basically now the total number of modes which exist are basically just the number of LM pairs we can have, right? So each mode is designated by these indices L and M, right? So each pair of L, each unique pair of L comma M will denote a unique mode, right? So we just want to see how many pairs, how many different L comma L values there can be. Right, so if you plot this on the ML plane, right, so you can see this is an equation of a line in the ML plane, right? So we plot this line like this. So the intercept on the M axis is, so when L is 0, right, you can see M is V over pi. And on the other side, so when M is 0, L is 2V over pi. So that's the range of values. So the maximum value L can take is 2V by pi. Maximum value M can take is V by pi. Right? So this would happen for L equal to 0. So for L equal to 0, you'll have all these M values. So 0, sorry, M starts from 1. So 1, 2, 3, all the up to V by pi, roughly. Right? And so on the L axis here, so that starts from 0, and then we have 1, 2. Okay, so we have a mode here for each integer point here. Right? Right? So for each integer point here, we have a particular mode, right? So you can see that we have one mode per unit area, right? So a square of side 1, right? So we have one mode per unit area. So basically, what is the total number of modes is basically the area of this triangle then, right? Because we have one mode per unit area. So right, and so the area of the triangle is straightforward. So half height. Right. So those are the total number of LM values that we have, right? But now if you also want to include degeneracy, right? So remember, there is a four-fold degeneracy for each LP element, right? So 2 from polarization X of Y, and then 2 from the sort of the mode distribution in the azimuthal direction, either sine or cosine, right? So each so to include the degeneracy, right? So this is including the polarization and the azimuthal degeneracy. So we multiply that by 4 to include, yeah. So for each LM there are actually 4 degenerate modes, right? So then the total number of modes including the degeneracy is this. Right, so you can see that, so this number is then, so the number of modes right is roughly 4V square per pi square, right? This number is more accurate for the higher the V number is. Basically where this asymptotic form becomes more applicable. Okay, but sort of the main point here is you can see it's proportional to V square, right? So if you recall when we were discussing the modes in the slab, right? Again, there was one-dimensional confinement, and there the number of modes scaled with V, right? So it basically every time, so there we had sinusoidal solutions, and every time V crossed by pi, we got another mode, right? So, so the number of modes in the slab case was proportional to V. And now here you can see now we have two-dimensional confinement, right? So now the number of modes scales with V square. Okay, so the increase in the number of modes, so the scaling goes sort of with the confinement. Okay, so for example, if I plot number of modes versus V number for slab, I get a straight line. For fiber, I get this. This is 1D slab. This is fiber, or any 2D waveguide in general would have quadratic. Okay, so there are different ways to estimate this number of modes. Again, so recall this is sort of an approximate expression anyway. So for example, in some of the books you might see like some other ways of approximating this, and you might see expressions like V square over 2. Okay, so you can see it's very close to that, but the main point is the scaling of V square. Okay, so I think that basically finishes most of our discussion on LP modes. Step index fiber, right? So, so we'll sort of now discuss a little bit about the exact modes in a cylindrically symmetric geometry like a fiber, right? So again, recall these LP modes were approximate solutions, but they work very well in the weakly guiding limits, again, where the index contrast is very small. But we'll just briefly discuss what are the exact modes and how they differ from these LP modes. So yeah, before we move on to that, any questions on whatever we discussed so far on LP modes? Okay. So we'll move on then. Right. So next topic is the exact vector modes. So they're called vector modes because, as we saw, like the wave equation is actually a vector equation, right? But we make this scalar wave approximation, right, for the LP modes in the weakly guiding approximation, right? Right. So recall our discussion. If you have the wave equation, something like this. Right. So this is a vector equation, right? And for Cartesian coordinates, we can sort of split this into three scalar equations: one for Ex, one for Ey, one for Ez. That's because the x, y, z vectors are constant vectors, right? So, like for example, if you look at the cross section of the fiber, the x vector is always in this direction, right? Doesn't matter where I am plotting this x vector. Right, so this unit vector is actually independent of position, so that's a constant. So that does not come into this derivative, right? So we can just take that out, and so for each x, y, and z component, we have a scalar equation. So in Ex, Ey, and Ez, right? So in Cartesian coordinates, that's why we can do this scalar approximation and solve for the scalar modes. But in the cylindrical case, right? So in a fiber, we have, of course, cylindrical symmetry. So if you want to work in R, phi, and z, right? So, but you can see R, right? So that is not a constant vector, of course, right? So depending on where I am, the R vector is pointing in different directions. Similarly, the phi vector is also not a constant vector, right? So for the R and phi components, I can't take that unit vector out of this derivative, right? Which means I can't just use scalar equations for Ez, E, phi, and R, right? So the equations are actually much more complicated if you want to do it that way, right? So in this case, the actual way to solve, as we sort of discussed briefly when we started discussing modes in the fiber, is so Ez, right? Z into the board, so that's a constant vector. Right, so for the Z component, we get a scalar equation in Ez, right? So that's rigorously correct, right? So we can have a scalar equation Ez. Similarly, in Hz, right? So these two equations are rigorously correct. But the R and phi components, we can't just do that. So R and phi components are in some way coupled to each other, right? So one way of saying that if you take the derivative of the R vector with respect to position, you'll get a component in the phi direction. Similarly, if you take derivative of phi vector with position, you'll get a component in the R direction. Okay, so to solve for the actual modes, what we do is first start with the z components, equation for the z components which are rigorously true, right? And now we can solve this in cylindrical coordinates just like we did, right? So now for the LP modes, what we did was we made the approximation of the TEM modes and then so assumed some polarization for the electric field like EX or EY and then solve this equation for the EX or EY, right? But that is not rigorously true as we see. So what we do is we start with Ez and solve, and it's the same cylindrical equation that we have. So we get solution for Ez like what we just saw, right? Bessel functions times sine or cosine. Right. So Ez and Sz will have that particular solution. Right. Another way to see where how LP modes are sort of not exact. This also we discussed briefly, right? So the boundary conditions are not satisfied clearly, right? Exactly, because so you can see that here the field is parallel to the boundary. So here the boundary condition will be the field is continuous, whereas here the field is perpendicular to the boundary. So the condition here will be that actually D, which is epsilon times E or n square times E, that is continuous, right? So actually there is no way that if you just have a function of R which does not depend on phi, like for example you have this Bessel function solutions, that cannot satisfy the boundary conditions everywhere, right, simultaneously. But basically what we said was for the LP modes that we are working under the approximation where n1 is almost equal to n2, right? So percentage difference between them is like less than 1%, let's say. So then this condition also, because n1 square is almost equal to n2 square, this condition is almost also equal to like field continuous. Okay? So we were working in that. But you can see that that is not rigorously true, right? And especially if n1 is more different from n2, the index sort of increases, then this is now clearly violated. Right? So one conclusion from that is you can see that the polarization cannot be completely linear. Right? So the true modes will have polarization which actually depends on position also. So they'll have inhomogeneous polarization. Right? There will not be just one particular polarization everywhere. Okay, so yeah, so basically we won't go through the entire procedure of how to solve for the modes exactly because that becomes very complicated. As I said, for most practical applications, the LP modes are enough. But just to give you, you should be aware of this if you encounter a case where you need to solve for the exact modes. Right, so so we get these solutions that we already found, right? So for example, this kind of Bessel function times right, so this is in the core. So now this is for Ez, okay? This is less than okay. Right, and of course times some propagation constant, which depends on this indices L and M, right? Similarly, you have Lz. So you have the same form of the solutions, right? Because again, satisfies the same equation, again, same boundary conditions. So the only difference is this amplitude here could be different, right? Now we have B, and basically everything else. Yeah. Okay, and so now we relate A and B again using the boundary conditions, and so we get some transcendental equation, right? In this case, so the boundary conditions would be, so for example, Ez and Nz are continuous at the boundary r equal to A, and then other boundary conditions would be, for example, E phi, right? So E phi will be continuous. So Z is into the board, so that's of course tangential. E phi is also tangential, but ER is not. ER is, you can see, perpendicular. So E phi will be continuous at r equal to A, but ER, not ER, but n square times ER will be continuous at r equal to A. Right? So we can use these boundary conditions. So from Ez and Hz, what we first do is find the other field components like E phi, ER, and then H phi, HR. Okay, so we can do that by again using the Maxwell curl equations, right? Right. So the problem was that we could not just from the wave equation solve for E phi and ER because again of this unit vector problem. So we start with solving for Ez and Hz, but turns out from Maxwell curl equations we can actually find all the other field components E phi, ER, H phi, HR just from Ez and Hz. Okay, so that turns out to be quite convenient, right? So you can try to do this yourself at home. So write down the Maxwell curl equation. So you could do this in Cartesian coordinates, or in this case you have to do them in cylindrical coordinates. So write the curl equations, right? And then so you get, so for example you get 6 equations, right? So 3, so R phi Z components for the del cross E equal to minus del B by del T, and then R phi Z components for del cross H equal to del D by del T, right? So using these equations of the different components, right, you can sort of manipulate them. So out of these now, Ez and Nz are known, right? So the only unknown components are 4, E phi, ER, H phi, HR, right? So actually you have 4 unknowns and you have 6 equations. So actually you don't even need all those 6 equations, just 4 of them are enough, right? So they'll be sort of like just linear equations in these, right? So you can solve those equations to find out the other components. So for example, you get equations like this. Right? So in terms of Ez and Nz, right, which we know, we can find, so for example, ER, E phi, HR, E phi, okay. So you can see you can get all these 4 components just from Ez and Nz. You can do this same thing in Cartesian coordinates also, but here of course because we have cylindrical symmetry we do for cylindrical. But in general, I'm saying for any waveguide, right? You can write the other 4 field components in terms of Ez and Nz, right? So for example, you could also have in Cartesian coordinates, you will have Ex, Ey, x, y. The equations will look slightly different, of course, because the curl derivatives are look different in Cartesian and cylindrical coordinates, but basically, yeah, so you'll get similar expressions. And the main point here is that, so now you can see that for any waveguide, right, which has 2D confinement, which means that, so the propagation direction is H in Z. Because we can write the other field components in terms of only Ez and Hz, both of them cannot be 0, right? So if, for example, we had Hz and Ez both 0, so then all the field components will be 0. So that will be like everything is 0, and that's like a trivial solution, right? So you can see that for any guided mode, from here you can see, for example, that you cannot have purely TEM modes, right? Right, so you either have to have Ez non-zero or Hz non-zero or both non-zero, right? If Ez and Hz are 0, then everything is 0 and there is no mode. So you can see that for waveguides from here that you cannot have purely TEM. Right, so you start from these solutions, right? Find the other field components, then use boundary conditions. Okay. So from that, basically, we can get relations between this A and B, and then try to solve for this beta using some transcendental equations. So now the transcendental equation that we get will be looks much more complicated, right? You can't write them with simply just like this ratio of Bessel function that we had. It will be like a more complicated. Of course, we have Bessel function, but the expression is much more complicated. But anyway, you solve that to find the these values of beta, right? And also relate the field amplitudes. So basically, we get two classes of solutions. Okay, so depending on how A and B are related. Okay, so this value of A by B. So for example, to B, that we get from again this solving this transcendental equation or from the boundary condition, right? So if so, you can see A and B. So basically, are the relative magnitudes of Ez and Hz. So if this is greater than 1, which means Ez is stronger than Hz. Okay, these are known as HE modes. Okay. So in general, basically from the equation we get both A and B non-zero. So both Ez and Hz will exist. Right. So not only do you not have TEM, you also don't have TE or TM. So if one of these are 0, then it's TE. Right. So for example, if Ez is 0, then you have TE modes. E is Fourier transverse. Right. But in general, both of them are non-zero. But the relative magnitudes are used to sort of classify the modes. Okay. So if Ez is stronger than Hz, they are called HE modes. Or if it's the other way around, they're called EX modes. Okay, so the first here, the symbol here denotes which component is closer to transverse, right? So here, for example, Ez is stronger, Hz is weaker. So that means the magnetic field is closer to being transverse, right? The longitudinal component is small. So we have H here first. In this case, Ez is weaker, so which means electric field is closer to being transverse. So that's why we have E here first. Okay, so Yeah, so these are closer to TM modes, right? So magnetic field is close to being transverse, but not exactly. And these are closer to TE modes. Okay, so this is in general that we get for L non-zero. Okay. So, but if L is equal to 0, turns out that if you use the transcendental equations, so one special case is if L equal to 0, then from transcendental equations, basically forces either A or B to be 0. So either A has to be 0, B will be non-zero. Both can't be 0, right? Again, from this argument that we had, both A and B can't be 0. Right, so in the case of L equal to 0, the transcendental equations are such that either A has to be 0 or B has to be 0. So if A is 0, you can see that that means SZ is 0, EZ is 0. Right, so this is a TE mode, purely TE mode, EZ is 0. Okay, so these are denoted as TE and the index will be 0, M, right? So L is 0, and then for depending on the M value, you will have some M. Right, so here these will have two indices, L, M, both L, M. Right, for L equal to 0, so it's either a TE or if B is 0, then it's TM. Right, so for the L equal to 0 case, which is no azimuthal dependence, we actually get either purely TE or purely TM. Exactly. But if L is non-zero, then both EZ and SZ exist, right? And just from the relative magnitudes, we say it's either EH or H. So that's the true mode. So now you can see that from these equations, right? ER, E phi, HR, Fi will not look like these, right? Some J L times cosine L phi, they won't look like that, right? So they look slightly different.